I think I should start posting a bit more, because I only have 2 videos on the channel, and the last post was about 1 week ago. And yeah, this is the Super Keck B, which is a particle collider in Japan. And I'm going there soon, sometime soon, and they actually allow you to visit it. So yeah, I've emailed them about it to see if I can get a tour. Hopefully, if they allow me to film, maybe I could upload it. But anyway, back to what I was studying. I've been busy with a writer's book. I actually skipped past. Well, no, I didn't really skip past. Oh no, I've been busy with Brewer's book. I actually was on Rider, this one, the first book that the professor gave me if you watched the previous video. But I found out that there's a lot of overlap between the topics, and I actually don't really like how he presents stuff on this. I actually much prefer Brewer's presentation, even though both are reasonably archaic. They are quite old and quite outdated, but it's okay. And they actually do things that Peskin and Schroeder doesn't. Like, they do a lot of transition between the Euclidean and Minkowski space via a Wick rotation, and I'm starting to understand why they do that. It's a bit more mathematically, I don't want to say rigorous, but it's a bit more sophisticated, I guess. It's a bit more comprehensive and less hand-wavy. So I don't mind it. I think it's a step up. And in fact, I'm gonna try and recount some of the things that I learned recently. Yesterday I spent quite a lot of time learning about the dimensional regularization. And it's only like 10 pages in the PDF, which kind of sucks, but it is what it is. Yeah, it's just some scrap paper. Anyways. Yeah, I have it written down here, and I'm gonna try to explain it, mostly to myself. And yeah, I guess we can get started. I'm using him as my camera stand again, and he's propped up on the TI-84 so that he gets just the right angle to view the board. Okay, we got it. Alright, so here is the Klein-Gordon equation that you get for 5/4 theory. If you go by the generating functional method, and you'll notice that you have an extra term here, and this term is actually infinite because it's a Feynman propagator at the point 0, and obviously this diverges when you evaluate it from negative infinity to infinity. It's not really obvious that it diverges yet, because you might know that we add the IE term thinking that maybe you could shift the poles of the real axis. So what that does is, say here we have the imaginary axis, and here the real axis. And there are poles here at plus minus m if we didn't have the I epsilon. But once we add I epsilon, what we're doing is we're actually shifting those singularities of the real axis, and then hopefully we can evaluate it. This is Feynman's prescription. There are many ways to shift the poles of the real axis. You could shift this one downwards also, or you could shift this down and this one up, shift them both up, and they all correspond to different kinds of green functions, but Feynman chose this one, so that's the one that we use. It also preserves causality, that's why Feynman chose it. It's not because he just liked it. Anyways, so you find out that you have an extra term, and you find out, and we'll show shortly that this extra term actually diverges, and that's not a good thing, because when you have an infinity in an equation where you didn't expect an infinity, then you have to somehow account for it. So, like I said, in traditional 5/4 theory, you wouldn't have this term, and you just have the d-L-13 and your mass term, and you have your field. This is the 5/4 field, and you have some extra order terms which we just ignore. And now we have this. So the way that renormalization works is that it says, well, instead of us having actually an extra term, we actually didn't have an extra term all along, but we just noticed that these two are actually our original term, which is why I put a bracket over. So this would be your total m squared in your classical Klein-Gordon field, and the B is called the bare quantity, BARE, which means like non-renormalized. So once we renormalize this, we hope that this would just equal to our old m square, and then we could do all our calculations like normal. But the issue for that is that now this bare quantity has to be infinite, and to account for that physical interpretation, you have to say that, well, this is non-observable, and these infinities cancel each other out to create an observable mass of the field. So yeah, it sounds a bit finicky, but I believe since in the early days it was considered a bit weird, and it was considered a bit suspect, but I'm pretty sure there's like a mathematical rigor behind it now. I believe it was developed sometime in the 1970s or late 1960s. So this is a completely mathematically sound method of getting rid of infinities. We are not just like subtracting infinity from infinity and taking it as if it makes sense. We are actually, it's actually quite a well-defined process. But for now, it will look, for introductory purposes, it will look a bit weird. So anyways, we're going to try to evaluate this Feynman propagator and show that we can actually get a finite quantity from it. And let's first show that it's divergent. For this part, we will have to consider. What do we have to consider? Yeah, I'm recalling, I'm not really teaching, it's more explaining to myself. I think we have to break this down. So how we break this down is, by the way, the slash notation is to indicate division by pi over 4. So if I do something like this, sorry, not pi over 4, 2 pi. What am I saying? 2 pi, so it looks like that. Anyways, so this volume element, it's a volume element, grows to the power of 3. So it looks something like like that. And the reason it does that is because it's a volume element in 4-dimensional space, and this is something like what you get when you evaluate a spherical integral. So you pull this out and then you get the dq left. And what you realize is that when you have this out, then you have your Feynman integral basically. I mean your propagator basically looks like you don't have the 4 now because you took it out. And then you have a q to the power of 3 in the numerator because this one goes on top. And then what you realize is that you have a quadratic power in the bottom, and then you have a third power on top. And so what it does, let me just erase that. What it does is that you now have your integral basically grows somewhat linearly, but not just linearly, it grows because of the absolute value, it actually diverges. So the integral actually looks something like that. And this obviously is a divergent quantity, and that's not a good thing because it's very hard to work with infinities. So what we like to do is we like to get a huge number, but get a huge number that is finite, that we can work with. So I don't think I need to sketch this out, but anyways, it should look something like that. the graph should look something like that. And if you take, obviously the limit is from negative infinity to infinity, and obviously if you get the area underneath, this graph is infinite. So there are a few ways that people have tried in the past to renormalize this quantity, to make it finite, in other words. And if you look at this graph alone, you can sort of get a few ideas. And the simplest idea is to set a cutoff. So instead of saying our limits are from negative infinity to infinity, we say, sure, maybe not infinite. We tell ourselves we're not evaluating for infinities, because in the lab, how do you test an infinite amount of momentum? Doesn't make sense. So we say, alright, we don't need to evaluate infinity. We just evaluate a super high energy cutoff that we will cut off in our lab parameters. And this high energy is called, we just label it big lambda. And so what it does is it restricts our area integral from negative lambda to lambda. And you do get a big area underneath, but the area is finite and it's something you can deal with. So this makes sense. And you set the parameters in your experiment, you only allow the particles to collide at a certain energy, and then you hope that this energy makes sure that your renormalization makes sense and that you don't get infinities. So yeah, it makes sense, and it works on the surface level, but the problem is that now your theory isn't gauge invariant, and it isn't, more importantly, it isn't Lorentz covariant. And that's a huge issue, because, well, if you don't have Lorentz covariance, you don't have relativity. So this is not, it's not a very, very useful method to deal with the infinity. And even if you're not talking about gauge invariance here, because we're just doing a 5-4 theory, it's still an issue down the road when you want to consider gauge invariant theories like electrodynamics and chromodynamics. So yeah, this doesn't really work, and it was sort of discarded. But there's something similar to this that you can do, and it's called a covariant cutoff. So it's good now because it's covariant. So you might think it solves the problem. And the way that we do this is, instead of limiting the integral from negative lambda to positive lambda, what we do is we multiply it by as many factors as we need. But you want to multiply it by something that's roughly equivalent to 1. So once again we have that lambda, and then we have let me just check that. Oh. Maybe I should write this in a different color. Let me just do that. Anyways, it's not very clear. Okay, so you can kind of see how this quantity that I'm going to write is roughly equal to 1. So it's not super illegal, I guess. So you're just multiplying it by this factor of negative lambda square over q square minus lambda square plus I epsilon. Yeah, that looks nice. Okay, so you can see how for low momentum, this basically works like a cutoff. It works like the previous method that we did. Because for low energies, for low momentums, you basically can ignore this, you can ignore this, and these two divide out to be equal to 1. So it's almost like we are multiplying everything by 1. And if you consider for large momentum q, the denominator becomes bigger than the numerator, and then this whole term becomes 0. So in a way, you're saying for lower q's, we can evaluate this integral, because this one is about equal to 1. But for larger q's, that's where we draw the line, and this one becomes 0. So this one becomes like it's like a monitor. It basically monitors your integral, and if your integral blows up, it just stops you from evaluating it. So basically, it's like a cutoff. It's called a covariant cutoff, and the reason it's called covariant cutoff is because it solves the issue of changing your limits. Because when you change your limits, you're not Lorentz covariant anymore. But if you do this, you are still Lorentz covariant, and you still get the nice cutoff effect. So what's wrong with this? The thing that's wrong with this is that it's not gauge invariant. And once again, if you don't have gauge invariance, you cannot use this method to consider more complicated stuff like quantum electrodynamics or quantum chromodynamics. So that's still an issue. So up to 1970s, this was still used, but once we found better methods, we just discarded this and we stopped using this method. So we've just discussed two methods of renormalization, and we've realized that both of them aren't very adequate. So here we need to introduce the third method, which we do use. It's called dimensional regularization. And I won't actually cover the part which gives the namesake, which explains why it's called dimensional regularization. I'm just gonna try and evaluate this integral, because once again, this video is more like it's more for my purposes. It's for me to recount how to integrate this. So anyways, what we do here is we are working in Minkowski space, and we are taking the mostly minus metric. So we just put it here. This is our metric. And what we're going to do is we're going to transition back to Euclidean space. And then in Euclidean space, we can manipulate the spherical symmetry to get a nice integral. And here we can actually generalize this to, instead of 4 dimensions, we're going to do 2 omega dimensions. We can actually consider an odd number of dimensions, but for now, to simplify things, we're just going to do even number of dimensions. So we're going to do our transition to Euclidean space, and the way you do that is via a wick rotation. A wick rotation, and when you do that, you get a negative I factor. In our metric, you should get a plus I factor if you go from Euclidean to Minkowski. But now we're going from Minkowski back to Euclidean, so we get a negative I factor. And we're just going to write an E subscript to denote that we are back in Euclidean space. And we don't need the IE factor, the I epsilon factor, because we are able to evaluate this exactly. So we don't need it. Okay, and for this, here we are going to now take the volume element of this. I'm actually going to erase everything. I'm going to write the integral, I'm going to term it as I, and I forgot to include the B subscript from previously. So I'm just including it here. And I expanded out the bar notation, because we're going to consider the volume element right now. And yeah, this is the volume element in 2 omega space, 2 omega dimensional space. And this is the volume of the unit sphere, which is equal to I omega over the gamma function plus 1. Yeah. And a thing to note is that since we're in Euclidean space, we don't need to put like the vector arrow on top, because in Euclidean space our metric is just all plus signs, and so there's no distinction between the time dimension and the spatial dimension. So we don't have a arrow right here. This is not necessary. In fact, it will be wrong if you added it, so we don't add it here. And what we do is we sub this into the integral, and we also want to make a little change, a little substitution, so that we can evaluate it nicely. The substitution that we're going to be making is yeah, this is just there's nothing physical that we need to talk about here. It's just a substitution technique, and we should get that this will give you our integration measure of this. And our limits now are not from negative infinity to infinity. It will be from 0 to infinity because we have the absolute sign. Yeah. And when you do that, you should get quite a long expression. So I'm going to pause the video again. Okay, so this is how the integral looks like after the substitution. And the limits here changed. And this is still 2 pi to omega. Actually, we can try to evaluate it here. Okay, so let's just look at them one by one. We have a 2 pi to the power of 2 omega here, and you have a pi omega here. So pi to the omega here is cancelled out, so you have a factor of basically 2 square pi to the power of omega, so that's 4 pi to the power of omega. Alright. And let's look at the MB, so the bare mass. So you have 1 here, and you have 2 omega minus 1, so now you have 2 omega. And from here you have MB squared in the denominator. So in total you should have M2 omega minus 2. And for K, let's see K. Actually, let's not evaluate K first, because we're integrating over K. So let's try to get the constants in front, and then we have K at the end. Okay. For 2, these 2 cancel out, and 2 here cancel out. And you can use the identity here that gamma omega plus 1 is omega gamma as a function of omega. So this omega should cancel out with this omega. You just have gamma omega in the denominator. And I guess we're left with K now, because we dealt with the pi, we dealt with the M, we dealt with the gamma. Yeah, it leaves us with the K. So let's look at the K. You have a negative half here in the denominator. So together with this, it makes it omega minus 1. And you have basically K plus 1 here, because we factored out the M squared. So on top should be e to the power of omega minus 1. And bottom should be K minus 1. Yeah, so this is actually a beta function. So this whole integral right here is a beta function. This is constants. So when you integrate this over dk, you should get, I'm not going to write out the constants here, so you should get kind of running out of space, omega minus 1. So if you can do a bit of the math mentally, this one should cancel out with this, and then they're basically done. So you can just, I'll write the solution. This one should be 1 minus omega, not omega minus 1. Anyway, this is the final result, and you can actually box this up. So this is a finite result that you get. And the thing to know is that this is actually, the stuff inside here should be an integer, should be a positive integer. So you actually have, for omega more than 1, you have to use analytic continuation to expand this out. And when you expand this out, you have to make sure that you don't mess up the mass dimensions. In other words, the units, not the physical space-time dimensions, but more the units dimension, because you have mass units here, and you have to make sure that you basically don't mess it up. That's where the term dimensional regularization comes from. Because what we do at this juncture, in order to evaluate this, is you try to remove the dimensions from this by dividing it by another mass term that is just like a dummy. So you divide it by the mass term, and then you expand this out, and after that you multiply back in the mass term. So that's where the name comes from. And with this, you can actually get a few more useful integrals. You could differentiate with respect to m, and you get another integral. You could differentiate. Now remember, we're working in k here, but if you transition back to q, you could differentiate with respect to q, you get another integral. Or you could do a substitution of like a shift, so q becomes q plus, let's say q prime, you get another integral. And all of these integrals are useful for evaluating your 1PIs, your one particle irreducible green functions, which are divergent, so you can get a finite quantity, albeit large, but a finite quantity that can later try and cancel out. So yeah, that's the first way of renormalization. And I know it's a bit long and it's all over the place, but the main purpose was to see if I actually understand some of this stuff and some of the integration. I think I achieved what I set out. And yeah, hopefully maybe it helped clarify a little bit for you. Because if you're using Ryder's book, Ryder? No, it's Brewer's book. If you're using Brewer's book, they're not too clear about it, and especially not the evaluating integrals part. So I hope I was able to provide that for you. Another thing, I realized I've been calling it a Brewer's book, but it's actually written by Bailin and Love, 2 people, and Brewer is the chief editor. But I'm gonna just keep calling it Brewer's book because it's easier to say one name. Yeah, that's about it. It's a long video. Thanks for watching. Bye.